think I've covered all the pages of this handout here in class. The last example was this one on page 4 about the water use. And I think I remember talking about that one as to why that was a split plot design and so forth and so on. So let me put this aside. And I have a note that I passed out this extra handout last class, and we went through this as well. You might remember it with the example about the grass clippings on the second page. Did we do this one? I thought we did. I thought we talked about this one. So there was another nice example of a split plot type of an experiment. And so I'll put that aside as well. Copied from another source about split plot designs. So here is the description of what's going on here with this experiment. It talks about the talks about how we run a replication or a block, and then within a replication, an oven temperature is chosen at random. That's the top variable here. And we have 4 choices of oven temperatures. And within a given temperature, chosen at random, baking time is also randomized. So if you look at this layout of the data here, and look at replication 1, apparently what they're saying there is that at random one of the oven temperatures is selected. Then when we get the oven set at that temperature, then we have to deal with this baking time. So what are we baking? It doesn't say that I can see. So anyway, we're baking something, but we can bake it for 5 minutes, 10 minutes, or 15 minutes. Now, how is that going to happen? So basically, what they're saying here is that you set the oven temperature, and you put 3 of the things in the oven, and then after 5 minutes, you randomly take 1 out. And then you wait a little longer, and after 10 minutes, baking time, you randomly select one of the 2 left to be removed at the 10, and then the third one is baked for 15 minutes. So in that way, you have at each oven temperature, you have an item baked at the 3 different baking times. Now that process is then repeated for each of the different oven temperatures, again in some kind of random order. And that finishes replication 1. Then we go to replication 2 and do the same thing all over again. And we do the same thing for replication 3 all over again. And so that's how this data might be generated. Okay. So if I try to think about a split plot experiment back in this kind of layout that was on my very first page, where does this appear in this example? I guess I would say in the first replication, here's the whole plot. Here's the second whole plot. Here's a third whole plot. And finally a fourth whole plot. So those are the whole plots in this layout. Then each of the whole plots is divided up into three smaller portions, or split plots as we would call them. So we would have 3 there. Again, this is balanced, so we have 3 in each case. These are the subplots. So we have plots and then subplots in this example. And then the same thing goes on in the second replication and in the third replication. So if that's the way the data is collected, and that's the meaning of the data, what does this source go on and do with the data? Well, it writes down a model, and I think this is the same model that we have in our handout. These pieces are the same. And we have that one, that one. We don't have all those terms in our handout model. What do we have in our handout model? We've got a term for the block effect, term for the A effect, block effect, interaction between A and block. Then we have B, then we have AB, and that's it. So in this layout here, we would have our replication like this. So we would have T, RT, and RT. Okay, that's doing fine. Then we have BK for factor B. Then this one we have, this one we don't have, and this one we don't have. So this model anyway is different than the one on the handout that I gave you first. And as I told you at that time, this happens with split plot designs. Different sources, different authors have slightly different ways of specifying a model. So okay, we can see a difference here with our model. Let it go. Then we have down here the calculation of the expected mean squares. Now you've seen this kind of layout before. There's this algorithm that's being carried out to figure out the right terms in the expected mean square. So there's not too many in this example. I don't think I'll do it here in class, but I'll say this is a good exercise for you to look at the numbers in these columns and see if you can produce these as well, so that you could figure out these expected mean squares for this example. Once we have these expected mean squares, we could look at them briefly here and say, well, if we wanted to test t, which is one of our main variables, the proper denominator is right there. if I wanted to test the, what else would I want to test? Maybe the TB interaction. Looking over here, the proper denominator would be this one down below it right there. And if I wanted to test B, which is another one of my main goals, the proper denominator for testing B would be this interaction right there. And so anyway, we use the expected mean square column in the same way that we have in the past to figure out appropriate F ratios. No change in the thinking here. Now I should say that this column of expected mean squares fits the model that they specified at the top of the page here. If you change the model, then this is going to change, right? So you can get different F statistics with a different model. Now, I'm not going to try to do another one to show you that. I'll just tell you this is what happens. So the way these expected mean squares come out is dependent upon the model equation that we're using. We need to have numbers. And so they have entered the same columns in Minitab as they're using in their model. So that's just a repeat right there. And here's the F statistics. If you check, these F statistics are the proper ratios. And we have actually for Minitab this layout of expected mean squares. And so it tells us that the proper denominator is 7, 7, 5, 7, 3, 7. So it kind of tells us what it was using for the denominators of these F statistics. So if we quickly look at these results over here, not significant, that one's significant, not significant, not significant. Well, that one we don't even have a test for. I don't know why that's there. But the 004 for a p-value, that is significant. And so that one we would have to mark. So anyway, do the F testing in the usual way to reach the conclusion. And that's what they're discussing here in this writing down below the table. Okay. Questions on that handout? Anything more I should say about it? Where we have the whole plots and then within them the subplots, and see if I can talk about some examples where this kind of situation would happen. As I mentioned to you before, the genesis of this idea of split plot experiments came from agriculture, where the big boxes were actually fields of land, and then the smaller plots were actually subplots of land, and they were going to do something different in those subplots, one to the other. So anyway, this idea came from agriculture. For instance, I might have a scene like this. Sorry, you'll have to put up with my artwork here. Factor A has 3 levels, and inside we have factor B at 3 levels. And so my picture might look like this. We have the whole plots and then the subplots. Right? Now let's suppose that factor A is, suppose these are actual plots of land. These are actual fields on a farm somewhere. And A refers to the type of fertilizer for the crop. Okay. Now, what's the B going to be? Well, I've got several possibilities to talk to you about. So as a first possibility, suppose I had 9 tree seedlings. And I had random select 3 of them and plant them in the leftmost plot. Then I select 3 more of these 9 and plant them in the middle plot, and the last 3 I plant in the rightmost plot. So these trees are planted in the subplots in that fashion, and then after an appropriate amount of time, depending on what type of trees these are, how fast they grow, what we're measuring as a response from the tree, and so on and so forth. After some period of time, we're going to make a measurement on each of the 9 trees. Okay. Now, if I do this, I'm going to have a number in each of these boxes here, right? I'm going to have a number there, a number there, a number there. And going to the second plot, I'll have a number there, a number there, a number there, and the same in the rightmost plot as well. So I'm going to have 3 numbers in each of the main plots if I do this. Okay. And so my question is this a split plot experiment? I wish I would have made this a little bigger so I could have actually written some numbers in there. Let me say these 9 tree seedlings are labeled 1, 2, 3 through 9. And when I randomly assign them to the main plots, maybe I assign tree 2, let me call it suppose T4 is there, then T8, and then T2. Then suppose it's T1, then T5, then T, what's left, 7. Then I have T3, I've got 4, 5, T6, T6, I've got 7, 8, and T9. To use a number for each of the trees helps me a lot in reminding me what's going on here. I have 9 different trees, and they were randomly assigned to these 9 positions to give me the data that I would have. This is a perfect example of what we referred to before as a nested experiment. Factor A is fertilizer. Factor B is an individual tree. And B is nested in A. So this is not a split plot type of a situation. It's a nested situation. All right, let's do something else then. Suppose I have the same layout again. I'll make it a little bigger this time so I can actually write it. Three subplots again in each whole plot. So we have something like that. And now A again is fertilizer. Type or level. That's applied to the whole plot. Now, factor B here is something different. Suppose it's type of seed. And we have three types of seeds that we can use. So what we do basically in carrying out the details of this experiment is that we'll go to the first whole plot, one on the left say, and we've got these three subplots, and we might put B2, B1, B3. We're supposed to randomly assign the levels of B to the available subplots. So maybe it'll come out something like that. We move to the second whole plot, and we again randomly assign the levels of factor B, and it might come out like B1, B3, B2. And we finally go to the third whole plot and do the same random assignment of B. We might get something like B3, B1, B2. So the subplots are going to be planted with the seeds as generated by this diagram. And so the growing season goes on. At the harvest time, we collect the result and make our measurement, whatever we're interested in measuring about these plants. So if we have two factors, factor A and factor B, that are handled in this way, this is an example of a split plot experiment. It just directly fits the standard agricultural scenario. So let's just say here, this is a split plot experiment. And so we would write down the split plot model for factors A and B. And, oh, by the way, I didn't say, with a split plot, you have to replicate. With a split plot, you have to replicate. So let's call this C equals 1 to do that. And then at a different farm, or in a different place at this farm, we do the same thing all over again with a second replication. And we may have a few more replications yet as well. But we must replicate this basic design to have a split plot data set. You can see that happening if you refer back to something. The second handout that I gave you, which has a generic nodal table for a split plot design down here at the bottom of the page, you can see this source is emphasizing what I talked about last time again. There's two errors. There's error 1 and there's error 2. Error 2 comes from the split plots. error one comes from the whole plots. And so, they have in this table nicely laid out expected mean squares and so forth. But the thing that I wanted to mention is that if you want to use this error one, notice this agrees true. Little a is the number of levels of factor A. What's that symbol there? R. It's the number of replications. If you did one replication, you get a 0 there. So you've got nothing in that line. You've got no error line 1 if you only have one replication. So basically with a split plot design, you must do replication. You read it right there.
Question.
Yes.
Does it matter if the replications are, say, 2 different time periods or one period over a greater area?
Well, those are kind of subjective judgments that one has to make in assessing the situation. I mean, ideally, you'd like to have the replications set up to be similar. So you wouldn't want to have these fields, at the top of the hill, and then in the next replication, the fields are at the bottom of the hill somewhere. The soil's probably different than everything. So you don't want to make the replications different in any way that's sort of identifiable. What does that mean? Well, it's very subjective, right? I haven't got anything concrete that I'm telling you about it. Just that we should set up the replications to be similar as seems reasonable to us.
Doctor, I have a question.
Yes.
Doctor, how could we recognize or how could we differentiate between a split plot and a nested design with random factors?
Well, let's see. In this number 1 here, the tree could be a random factor. In fact, it would be. When you're trying to decide whether a factor is fixed or random, you always ask the question, do I care specifically about the levels of this factor? Yes or no? If you say yes, you have a fixed effect. If you say no, this factor is just representative of a bigger population, then you make it random. So deciding whether the factor is fixed or random usually is decided by that question. Am I interested in the specific levels of this factor? Yes or no? And that'll tell you whether you have fixed effects or a random effect to work with. So in the first example here with the tree, I think naturally this would be random. Because I don't care about these particular trees. They're just surrogates for the population of trees. Does that make sense? If I come to item number 2, it looks like this C type would be a fixed factor because I'm sure that I would care about the 3 types of seeds. And I can't think of any situation where if B was the C type, that I could somehow get E to be random. I can't seem to force it into the context in any kind of way. But I could have some other kind of factor there. Well, let's leave it. The example stands as it is. A very similar example, again from agriculture. Suppose I have the whole plots. Which are fields of ground. And A equals 1, A equals 2, A equals 3 is a variety of corn. We have 3 varieties of corn that we're studying in this experiment, and they're going to be planted separately in these main big plots. Now, inside the main big plots, we're going to have let's just say 4. Factor B is, let's say, manure. Amount, type, whatever. So 4 levels of manure are going to be applied to the subplots. And then that'll go on in each of the whole plots down the road. So we have 2 factors, the variety of corn that we're planting on the big plots, and then in the subplots, we're doing different levels of manure on the plants. Again, as you see, this is a standard agricultural type situation, right? And so this is the type of situation where split plot designs were designed for. So it fits perfectly. This is, again, a split plot scenario. Use the split plot model and the analysis of variance table that comes out of it. If you look at example 3 and compare it to example 2, you'd have to say, these are the same. There's no functional difference between example 2 and example 3. They're the same thing going on. I guess I've switched the fertilizer. Up here it's A, down here it's B, but that's not critical, right? So 2 and 3 are essentially the same scenario for generating a split plot instead of A. Now, let's come back to this number 2 again, and let's do this in yet another way. So instead of doing 2 as described here, where A is fertilizer and B is seed type, suppose we do it in a different way. So let's call it 4. This is going to be the same variable as 2. So A is, what was it? Fertilizer. Type or amount, whatever we're measuring. And B is seed type. Now, suppose in collecting the data to study these 2 factors, I do the following. So there's a plot of land. Oh, let's suppose I have 3 levels for A and 3 levels for B. So there's a big plot of land, and what I do is to divide it up into 9 portions. So let's suppose I divide it like this, and then horizontally like this. Now if I have 3 levels for A and 3 levels for B, 3 times 3 is 9. That's why I'm dividing this line up into 9 parts. Okay. Now apply the treatments to these 9 subplots. So, and do this at random. Okay. So maybe when I do this at random, I'm going to put here A2 with B1. Maybe here I'll have A1 with B3. Maybe here I'll have A1 with B2. And here I'll have A3, say, I'm just making this up, kind of mixing up the subscripts here. A3 with B2. And here I'll have A2 with B1.
You already have that one.
Ah, thank you. How about putting it with B2?
That works.
That work? Okay. Then let's see, I've got, let's try third 3 here with a B1. Then I'll move down here and I'll try an A3. I've got 3 A3s now. And then I need to have a, can you have a B2?
For a B1, it has to be B3.
Pardon?
B3. Be good.
B3 would work, okay. Then I could have here, I've got A3, 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 A1. I need another A1 somewhere. So maybe it's there. And then for B, I have to have B1, I guess. And finally,
A2, B3.
pardon? A2, B3. Well, anyway, you see what I'm doing, right? I've got these two factors, A and B, and I've got to apply them to these 9 plots of land. And I'm going to do this at random. So I did it at random. It didn't look very random to you, perhaps, but it really was. So I get data that looks like this. Now, you can visualize then, the next step is there's going to be a number in each of those 9 cells. I'll have something that looks like 10.2, 5.9, 11.1, 8.3, 11.1, again, 12.2, and then there'll be 3 more numbers there. So that's what my data is going to look like, right? Now, this could be, if you like, replication or block 1. And I could repeat this again with another plot of land, time and money for it. So this is the idea anyway. Now, if I get data that looks like this, is it a nested design? Is it a split plot design? No. What is it? Well, we don't have a name for this kind of design, but I guess I would just say this is a 2-factor ANOVA model. Okay. So the model would have a term for the effect of A, a term for the effect of B, a term for the interaction between A and B, and then that's it. So the usual 2-factor ANOVA table that we talked about way back quite a while now would be used for data that was collected like this. Now, yes,
What if we have 3 replicates?
pardon?
What if this one comes with 3 replicates?
Here we have what?
We have 3 replicates of this, what we have done. Will it still be a 2-factor ANOVA?
Yep. Now, when I wrote these numbers down like this, the columns aren't factor A, the rows aren't factor B. A and B are all scrambled up in these numbers, and we have to unscramble them if you wanted to write down a table of data where the columns refer to factor A and the rows refer to factor B. You could do that, but I didn't do it here. At the moment, A and B are all scrambled up in these numbers. I didn't answer your question directly. What was your question?
I was saying that what if we have more replicates? Assuming that we have 3 replicates, will it still be a 2-factor ANOVA?
Oh, sure, we've had 2-factor ANOVAs where we've had, in fact, almost all of our examples had more than one observation per cell. At this point, I have 9 cells. I have 1 observation in each cell. But if I had another replication, then I could get 2 observations in each cell. And we've analyzed data that looked like that way back a month or more ago. In fact, that's on the material for the testing experiment. So check that out again. Is that enough said about what I wrote there? It's kind of clumsy. I apologize for that. But I'm basically trying to say that we can get data on 2 factors A and B in a manner like this, which isn't nested, which isn't split plot. It goes back to the earlier ideas of just simply a 2-factor ANOVA problem. Now, nobody's going to let you do the experiment this way because it's too hard. Remember, factor A was the fertilizer choice, and B was the seed type. Was that what it was? So suppose we got to do this. So we got to get the field. We got to mark off the 9 sections, and then we got to come here and we say we got to use what was it, fertilizer type 2 in there, go out the lines, and seed type 1 in there, go outside the line, and then stop. Then we move over here and say we use fertilizer type 1 in there, go outside the lines, seed type 3 in there, and now we change our machines again, right? Because we've got to, we've got machines that are distributing the seeds and the fertilizer. So we move over here and do A1 and B2, and then we keep going here, 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 here. The problem with doing an experiment like this is that the farmer has to change around the equipment too often. So if you asked him, would you prefer to do it like method 2 here? He'd say, sure, this is going to be a lot easier for me because I take A, the fertilizer, and I apply it to this whole big plot of land all at once. And then A2 to this whole big plot of land all at once. And A3 to that whole big plot at once. And then once I've got that done, I've got to deal with the seed type in these subplots. And that's something I can't avoid. But anyway, I have to do that as well. So anyway, there's less monkeying around with the equipment. Design the experiment in a split plot fashion as opposed to the other way. So that's wave 4. All right. Let's move off of farms for a moment here now. Suppose factor A refers to hospital. So in a given city, there are 3 different hospitals, or maybe in a given county, there are 3 different hospitals, or whatever. There are 3 different hospitals, and this is going to be one of the factors that we want to study. Now, what else do we want to study? Well, let's see. I want 4 subplots in these main plots. So I guess I could do it in several ways. Let's just do it this way. All right, now suppose we're studying a certain type of surgical procedure. And there's just one surgical procedure. That's going on here. And what I do, I find 12 patients that need this procedure. Think of them as having a number assigned to them. 4 of these patients are randomly assigned to the first hospital. So this might be patient 7, patient 1 is maybe over here, patient 2 is here, patient 3 is here, patient 4 is here, patient 5 is here, patient 6 is here. What have I got left? Patient 7, patient 8, patient 9, patient 10. I'm not getting 12.
You have 2 patient sevens.
I have what?
2 patient sevens.
That's my trouble. All right, so let's change this 7 to
11.
11. I mean, this is 12. Okay, so you see in a way what I'm trying to do. I've got to have these patients, 12 patients assigned, 4 per hospital at random. So it's going to be something like this. Now, if I look at this again, and you think about the situation, you should say, aha, I recognize this as nested. Factor B in this layout would correspond to the patient. Okay. So this would be a nested experiment. Factor B, the patient, is nested in factor A, the hospital. Now let's suppose we don't do it that way. Let's keep going and change this around a little bit. So here's hospital 1. And there's 4 subparts. Here's hospital 2. And there's 4 subparts. We finally hospital 3. Side. Refers to a hospital, as in 5 above. Now, what am I going to do on these subparts within the given hospitals? So let's let E be, what should I call it? The surgical procedure. So in number 5, I didn't worry about the surgical procedure. All the patients were going to get the same surgical procedure. When I'm coming to 6, factor B is the type of surgical procedure. You know, I don't know what this surgery is, but if it's something like heart surgery, there's more than one style of heart surgery, depending on the physician and his or her background and training and so on and so forth. So that's what I mean by factor B, the type of surgical procedure. Now, what I do to continue this example is at each hospital, we find 4 patients that need the surgery, understood here. You're not going to just grab somebody out in the hall and drag them over to their operating room. You find 4 patients that need this surgery at each hospital, and they're going to go there at random. 4 are over here, there at random, and 4 are here, there at random. So when I've done this, I've got 4 patients at each hospital, and I'm going to use each of the surgical procedures once at each hospital. So for example, I didn't write it in here. This could be like B2, B4, B4, B3. Surgical procedure 2, surgical procedure 4, surgical procedure 1, surgical procedure 3. And then we do the same thing over here. B4, whatever. B1, B2, and finally B1, B4, So what does this picture say? It says that, well, at each hospital, I can see that I have each of the B's occurring once. So that means at each hospital, I'm going to use these different surgical procedures on one patient. Now, you can't use the procedure more than once on a given patient, right? So the implication is I have to have selected 4 patients here to be participants in the study at each hospital. And then we decide which surgical procedure is going to be assigned. Now, so what's the data going to look like when I'm finished? Well, in each of these little boxes, I'm going to end up with some kind of response measurement. So somebody's going to make a measurement as far as the result of the surgery. Maybe they're measuring some physical characteristic related to, I don't know, blood pressure, related to pain level, or whatever is appropriate. They might measure numerous things, as a matter of fact. But anyway, they're going to measure some response, and so in each of these little boxes, they're going to have a number. And so there it is. Now, this is like replication 1. I have to do this again. I have to have at least replication 2, and preferably a couple more. So the experiment has to be replicated to have a split plot of the data. Now, when I was thinking about this example, it occurred to me after I was kind of done with it, that this medical hospital type situation is really exactly like the agricultural examples. In the agricultural examples, this was a field of land, and these were subfields. This was the second field of land, and these are subfields, so the same thing over there. How do I get this hospital to match that type of scenario? Well, that was the question I asked myself, and I said, well, I could think of the hospital as consisting of piles and piles of patients that need this surgery. And what I have to do is to say, okay, the patients that are at hospital 1 are there, and similarly the patients that are at hospital 2 are in the second big plot, and so forth. Then once I've got that plot in mind, I've got to pick these subplots. Now these subplots here are going to be just one patient, right? So that's the size of the subplot. And basically what I'm doing is I'm selecting 4 subplots from the available stuff that's here in hospital 1. I'm selecting 4 patients, assigning them to get this or that surgical procedure that's directly analogous to in the farm experiments. Where these were plots of ground and we were assigning, like seed type or something to the plots of ground. In the hospital, we're assigning surgical technique to the patients. So it seemed to me to be identical, very analogous in this hospital situation, as opposed to the agricultural situation. So anyway, my bottom line is, do the data this way. Excuse me. And you'll have split plot data. A non-agricultural split plot data. If you try to look around through textbooks to find non-agricultural examples of split plot data, you're stuck. I think almost all the textbooks deal with agricultural contexts. Questions, comments on that? Okay, so there I've tried to give you some thoughts about examples, and we can finish up today with this. Okay, here at the bottom of the page it talks about oats experiment. We're going to talk about the yield of 3 varieties of oats, that's factor A, and 4 different levels of manure. Okay. This was an experiment described by Gates in his famous paper. Area divided into 6 blocks. Those would be for the replication, I suspect. Each of these was then subdivided into 3 whole plots. And the varieties of oats were sown in the whole plots according to blah, 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 blah. Each whole plot was then divided up into 4 split plots. And the levels of manure were applied to the split plots according to the randomized blah, 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 blah. So turning the page, we see the data. And so the first thing you can see is that we have six replications. 1, 2, 3, 4, 5, 6. What's in one replication? Well, the way this is laid out, the level of factor A, the variety of oats, is over here on the side. 3 varieties of oats. And then the level of B, which is the manure, there's 4 levels of manure. So there should be, for each level of A, there should be 4 manures. And I guess there is. 1, 2, 3, 4. For the next level of A, there's 1, 2, 3, 4 manures, and so forth down the line. If you wanted to write this data out like I have in my examples, I had put A on the top. As to the variety of oats. And so those are the whole plots. And then these have to be divided up into 4 parts. Maybe I'll just simply do it with horizontal lines. And these subplots are going to get a different manure treatment. We've got 4 manure treatments to choose from. So we're going to apply those 4 manure treatments at random for those 4 subplots. And then in the next whole plot, we do the same thing. 4 subplots, apply the 4 manures there. Finally, the last whole plot, 4 subparts, apply the manure at random there. So this data laid out in my style would look like this, but it's the same thing. This is the way this source chose to lay it out. Okay. And on the 3rd page, we see the split plot analysis of variance table. Notice the dividing line here. Above the line is whole plot information. Below the line is subplot information. And they talk about having a whole plot error. And they talk about having a split plot error in this source. Okay, well anyway, in the ANOVA table for a split plot design, there are 2 error terms. And, one for the whole plot stuff, the other for the split plot stuff. So you can check how the denominators were being used, although in the writing on the page here, you can see what they're talking about in forming the F ratios. This source doesn't list the expected mean square column so nicely as other sources do. Kind of like that, really, but this source doesn't do that. Well, a quick comment here. Multiple comparisons. Suppose we wanted to, in our model, estimate these differences of alphas. Use the differences of the sample things in the obvious way. Or we wanted to estimate the difference between two betas. Now, substituting in the means just gives us a single number estimate. If we wanted a confidence interval, we could choose to do, for example, Bonferroni or Tukey or something like that. And so on the following page is some calculations of those confidence intervals. And I think these are going to be simultaneous, although I don't spot here which method are they using. I must have said it on the previous page. So what does that import? It basically says, well, in split plot experiments, you can go on and do estimates and confidence intervals for the parameters in the model and use the usual stuff. You don't change anything that you know how to do, just use your usual stuff for that purpose. Okay. Well, that's all for today, so let's leave it there.